Hi, this is Jack Ng from Achevas, and today in this video we are going to be looking at Singapore Cambridge A-Level exam H2 Math Paper 2. And in H2 Math Paper 2, it comprises of two sections, Section A and Section B. Section A will be all the pure math questions, and in Section B, it will be all the statistics question. And in this video, we are going to be focusing on Section A. So all the pure math question, let's take a look at the first question together. It is an integration question. And for this question, we are supposed to be integrating x over square root of x plus 2. And in order for us to integrate this, the question actually gave us a help in terms of substitution. We are supposed to be making use of the equation u is equal to square root of x plus 2. So the objective is to try to replace all the x that is here by u. And the first expression that is probably the easiest to replace is going to be the denominator, because square root of x plus 2 is simply going to be equal to u. And we also want to replace the x in the numerator. So let's try to make x a subject here. We will square both sides. This is going to give me an x plus 2. So x is going to be equal to 2 squared minus 2. And that's what I'm going to do for this x here. We will replace it by u squared minus 2. And dx, we are also going to try to replace this dx. So to replace dx, we are going to work out an expression for dx du, which is 2u. So dx here will be replaced by 2u du. This 2, I am going to take it out of the integration notation, and u can be cancelled. We are going to be left with a very simple integral. It is just like a secondary school's integral. This will be u to the power 3 over 3 minus 2u plus c, okay, after we have integrated it. But let's not forget that we will still need to replace all the u by its corresponding expression for x. So this is going to be 2 over 3u to the power 3 minus 4u plus c, which is going to be 2 over 3u, which is square root of x plus 2 to the power of 3 minus 4 square root of x plus 2 plus c. This is for question number 1. Let's take a look at question number 2. Question number 2 will involve a cylindrical cylinder. And according to what the question says, this cylinder has a base area of 0.9 meters square and there's a height of h meters. Let me just draw a quick diagram of this cylinder, okay? So we are looking at something that is like this, where the height is, according to the question, h meters, and the cylinder has a base. Let me just draw it this way. The cylinder has a base which has an area of 0.9 meters square. So according to the question, water is going to be poured into this container at a rate of k liters. So k, it is in liters. K liters per second. So k liters per second, and the container is going to be filled totally within 72 seconds. Okay, that's what the question says. And we are supposed to, in part A, show that k is equal to 12.5 h. So we're going to try to look at the total capacity of the water. Is it water that we're talking about? Yes, we are filling in water. So we are going to look at the total capacity of the water and also match it to the total capacity of this cylindrical container. So for the amount of water that is going to be going in 72 seconds, it is going to be k multiplied by 72. And this should be equal to the total capacity of the cylinder. And that will be base times height. 0.9 multiplied by h, but this will just be in meters cube. And k, which is in liters per second, multiplied by 72 seconds, is going to be in liters. So we need to do a conversion. And the question has already given us the conversion, which is 1 meters cube is equal to 1,000 liters. So I'm going to multiply this by 1,000, which means that k over here is going to be equal to 12.5 h. And this is what the question wants us to show. Next, The question went on to say that the container is emptied and we are going to be pouring water into the container again, and this time it is going to be at a rate of kT liters per second, where T is the time that is taken for the water to be like filling in seconds. So from K, it becomes now a KT. This is the rate that the water is going to be filling the container. So if I were to just use black color to represent, like water that is going to be poured in, that is already inside the container, and I'm going to call the volume of the water that is inside as V in liters, okay? Which means that in part B, what we are given is that the rate of change of the volume of the water that is in the container is kT. So that means dV dt is going to be equal to kT. And what we are supposed to do is to find the time that is going to be taken to fill this container. So we need an equation that is in terms of V and T. Okay, because we know how much water will be required to fill this container. The container, according to the question, is going to be emptied. So the amount of water that's going to go in is going to fill the entire capacity of the container, which means that the total amount of water by the time the container is going to be fully filled is going to be this, 0.9 times H times 1000, which is equal to 900 H. So this is the capacity of the whole container, and this will be the amount of water that is going to be inside. Okay, so we need an equation that is in terms of V and T. We are going to solve this differential equation. So V is going to be integration of kT dt. So this is going to be equal to kT squared over 2 plus C. And according to what the question is telling us, the container is going to be initially empty, which means that when T is equal to 0, V is going to be equal to 0. So K 0 squared over 2 plus C is equal to 0. This tells us that C is actually just going to be 0, which means that the volume is going to be equal to, volume is here. So volume is going to be KT squared over 2 plus 0. It is going to be this. And we are going to let this volume be the total capacity of the container, so that the water is going to be totally filled, right? So that the container is going to be totally filled, not the water. The container is going to be totally filled with water. So we're going to let the container be totally filled with water by letting this be equal to 900 H. Okay, so we're going to be going for this, and we are supposed to find the time that is taken. So we are supposed to solve for T, but it is going to be in terms of K and H. But we do have an alternative in writing K. K is 12.5 H. So I'm going to replace this by 12.5 H. Then T squared over 2, this is K, is equal to 900 H, which is good because then this H and this H can be cancelled. We will be looking at T squared to be equal to 144. So T is just going to be equal to 12. Since T is the time, it cannot be negative. Okay, this is going to be for part B. Let's take a look at the next part. The next part is such that we are going to have yet another way of water filling the container. Okay, the container is emptied again, water is going to be poured in again. So the rate is going to change, okay? The rate is going to be changed to kT plus 25 liters per second. And the container this time is going to be filled in 10 seconds. We are supposed to find the height of the container, H. We are supposed to find this. So according to what the question has given to us, dV dt here is going to be equal to kT plus 25. So once again, we do need an equation that is going to be in terms of V and T. We need to solve this differential equation. V is going to be integration of kT plus 25. So V is going to be equal to kt square over 2 plus 25t plus an arbitrary constant. We have used c previously, so let me go for a d here. And because the question mentioned again that the container is going to be emptied when water is going to be first poured in, so by making use of that piece of information initially when t is equal to 0, v is going to be equal to 0. So we will have k times of 0 square over 2 plus 25 times 0 plus d. This is equal to 0. This tells us that d is going to be equal to 0. So v is going to be equal to kt square over 2 plus 25t. And when t is equal to 10 seconds, the container, according to what the question says, the container is going to be filled. And for the container to be filled, the capacity is equal to 900 H. So when t is equal to this, v is going to be equal to 900 H. And that will be k, t is 10 square over 25 plus 25. T here is going to be equal to 10. This is going to be 900 H. And for k that is over here, this k that is over here, we are going to be making sure that we need to replace this k, okay? We need to replace this k and we're going to make use of this that is given to us. So making use of this, we will be replacing k here by 12.5 H multiplied by, this is 100 over 25, so multiply by 4 plus 250, this is 900 H. It is a good equation because with this equation over here, we have one that is in terms of just H. So if I were to bring all the H over to one side, we will be getting, oh, I've made a mistake over here. It is actually kt squared over 2. So this is actually 2. Let me change this a bit. So this line here, it is supposed to be 100 divided by 2. So this is going to be equal to 50k plus 250. This is 900 H. And this k here, we are going to replace it by 12.5 H. Okay, so it is going to be 50. This is 12.5 H plus 250. This is equal to 900 H. Okay, so we have an equation in terms of H. We can solve for H, bring all the H over to one side. That will be giving us a 275. H is equal to 250. And H here is going to be 10 over 11. Okay, this is for question number 2. Let's move on. Let's take a look at question number 3. So in question number 3 over here, we have 3 complex numbers. Let me write down the 3 complex numbers. We have Z1 that is given to us as 3 minus I square root of 3. We have Z2, which is half e to the power of I, 2 pi over 5. And we have Z3, which is Z1 multiplied by Z2. We want to find the exact modulus and argument of Z3 in part A. So to do that, we are going to first change this into the Euler form, which will make it easier for us to be multiplying it by Z2. So looking at this, in order for me to change this Cartesian form for Z1 into the Euler form, I'm going to make use of its representation on an Argand diagram. So for this, it is going to be on an Argand diagram. It will be represented by something that is like this. 3, it is going to be on the positive real axis, and negative square root of 3 will be on the imaginary axis. So the modulus of Z1 is going to be this length over here, the length where this point is with reference to the origin. So this will be by Pythagoras theorem. It is going to be square root of 3 square plus negative square root of 3 square. This is square root of 12. 12 is 4 times 3. So I can also rewrite this as square root of 4, which is 2 square root of 3. And the argument of Z1 is going to be this angle over here. And this will be negative tangent inverse of this basic angle, which is tangent inverse of square root of 3 over 3. So this is negative pi over 6. We are going to be getting we have gotten a special angle over here. So this is telling me that Z1 is going to be 2 square root of 3 e to the power of minus I pi over 6. So this makes it like way easier for me to find Z3. Z3 is going to be equal to Z1 multiplied by Z2, which is equal to 2 square root of 3 e to the power of minus I pi over 6. This is Z1 multiplied by Z2, which is half e to the power of I 2 pi over 5. So this 2 and this 2 can be cancelled. We are going to be left with a square root of 3 here. And for the power of e, it is going to be I of minus pi over 6 plus 2 pi over 5, which will be giving us a square root of 3e to the power of I 7 pi over 30. Okay, so looking at this, which is Z3, we can then answer the question because the question is requiring us to find the modulus of Z3 and the argument of Z3. So the modulus of Z3 is going to be this over here. It is square root of 3. And the argument of Z3 is this over here. So this is 7 pi over 30. Let me just write down this information for us here, okay? Because we are going to be reusing it. I think it is going to be definitely useful. So let me write it down. Z3 is this square root of 3 e to the power of I 7 pi over 30. Right, 7 pi over 30. And as for Z1 we have also converted it into the Euler form. I might as well also write it down here. So Z1 is a 2 square root of 3e to the power of minus I pi over 6. Okay, so this is our Z1, Z2, and Z3 in the different forms that we have just calculated. Okay, so for this that we have here, we are going to make use of it to work on part B. In part B, we are going to be sketching representation on an Argand diagram to showcase complex numbers Z1, Z2, Z3. And because we are not able to be sketching the complex numbers on an Argand diagram, so we will be sketching representations of them. And I'm going to use points A to represent Z1. I'm going to use point B to represent Z2. And C will be helping me to represent Z3 on the Argand diagram. Let me draw a bigger one here. Imaginary axis and the real axis. Let me go for this. Okay, so we have an imaginary axis, we have a real axis, not the nicest drawn, like not the one that is the most nicely drawn axis. I can see that it is a little bit slanted, but okay, I think it is still fine. So let's draw point A, which is representing this. So this point here is going to be 3 and negative square root of 3. So it's going to be in the fourth quadrant. The distance of it away from the origin is going to be 2 square root of 3, which I can compare easily with this square root of 3. Because the distance of point A from the origin is going to be 2 times the distance of point C from the origin. So I think I'm going to make use of the Euler form. It seems to be easier. So let me go for this particular point here to represent point A. Sorry, this point here, which is going to be point A, which will be representing Z1. So if I were to just do a dotted line all the way until here, this distance here is going to be a 2 square root of 3. And the angle, which is going to be the argument, is minus pi over 6. So this is going to be representing Z1. As for point B, which will be representing Z2, The modulus is half, so the distance of it away from the origin is half. Half is 0.5. Square root of 3 is equal to 1.7 something. So the distance of this away from the origin will be smaller than the distance of this away from the origin. So let's take note of that. And the angle is 2 pi over 5. Okay, it's harder for me to imagine 2 pi over 5 in radians. Okay, so I did a conversion, 2 over 5 multiplied by 180. It gives me a 72 degrees. So let's say here, okay, somewhere that is looks like a 72 degrees. So let me go for, let's say, this point here to represent point B. And this distance here is going to be half. The argument is equal to 2 pi over 5. Okay, this will be point B, which is going to be a representation of Z2. And we still need a point C to represent Z3, right? So Z3 is this. The distance of it away from the origin is about half of this, but longer than this. So maybe like somewhere here. Okay, and 7 pi over 30, I did a calculation, so it is like 42 degrees. So somewhere like a bit like 45 degrees. So maybe somewhere around here is a good enough point for me to be using to represent C, okay, which is a distance that is longer than this, but it is like about half, okay, of OA. So for this over here, this is going to be square root of 3, and the argument that we are talking about is 7 pi over 30. This is going to be for part B. Okay, let's move on to part C. And for part C, we are going to be trying to find out the smallest positive integer that is going to be giving us z3 to the power of n to be a purely imaginary kind of number. Okay, so the first thing that we definitely want to find out is what exactly is z3 to the power of n. So for z3 to the power of n, we will be making use of z3 in the Euler's form. So square root of 3 e to the power of I 7 pi over 30. This is going to be to the power of n. It is easy for us to compute. It is going to be square root of 3 to the power of n. Then, just like indices, I 7m pi over 30. I'm going to re-express this into the Cartesian form or the trigonometric form. So this is going to be square root of 3 to the power of n. Then we will have a cosine 7m pi over 30 plus I sine 7m pi over 30. Okay, so we have this. And because the question says that z3 to the power of n is supposed to be purely imaginary. Okay, so for it to be purely imaginary, so it is going to be just this portion, which means that this portion over here, okay, this is always positive. Okay, so it can never be 0. So for this to be always imaginary, this portion here must be equal to 0. So you will have the I portion, only the I portion. Okay, so that is what we are going to do. We are going to let the real part of z3 to the power of n be equal to 0, which is going to be cosine of 7n pi over 30 to be equal to 0. I mean, of course, we can still write in the square root of 3, the whole thing to the power of n, but it is not necessary because, like what we have just explained, this is always going to be positive. Okay, so it is impossible for this to be 0. So in order for this to be 0, this is the only one that is going to be 0. So let me erase this, but it is definitely not an issue if you were to write down this together with this. You're going to be ending up with this anyway. And making use of what we have in our topical outline on the Achevas TV, we know that for this case here, 7m pi over 30, in order for cosine of this angle to be equal to 0, 7m pi over 30 is going to take up a form that we shared on the Achevas TV. It is 2k plus 1 multiplied by pi over 2, where k is some integer value. It is an odd number multiplied by pi over 2. Making n the subject, pi and pi can be cancelled. Making n the subject, we will have a 15 over 7, 2k plus 1. So this is the format of n that is going to be giving us z3 to the power of n to be purely imaginary. And we want n to be an integer value. In fact, we want to find the smallest positive integer value of n. So in order for me to find that, we are going to substitute different integer values into here to see what are the possible values for n. I think to substitute this in, the easiest way is for us to make use of our graphing calculator. So let me try to bring out my calculator, and I'm going to be planting this 15 over 7 2k plus 1 into y1, which I've already done so. And then we are going to let our calculator substitute and replace this x by integer values by going for second graph to trigger table. Okay, so these are all the values. These are all the different k's. Okay, and which will be giving us the different n's that is given to us here. A little bit hard for us to see because it's in fraction, so no problem. We can still leave it in fraction, but let me just do a quick tweak to this by converting this to decimal. Okay, so I'm going to just go all the way to the end, converting this to decimal. Let me just generate the table again. Okay, now it is easier for us to see. In fact, we start to see the first integer value for n already. Okay, let's just code a few of them. This is 1. Let's see whether there are any more before this. Okay, before this, oh, we see another one here. Okay, negative 15. Okay, that's actually not what we want, because according to what the question says, we want positive integer values for n. But I'm going to still code it here. So this is going to be one of the integer. Just now we saw another integer is 15, which is this over here. Let's see whether we will get any more integer after this 15. Okay, let me just press a little bit more. Okay, here we have another one, 10. When k is equal to 10, n is equal to 45. So these are the few integers, and we are quoting this because the one that we want is this 15. So therefore, the smallest positive integer value of n is going to be equal to 15 over here. The question went on to ask for more things. Let me just take a look. The question says that we are supposed to state the modulus and argument of z3 to the power of n. So for this value of, z3 to the power, we are supposed to quote the modulus and argument of z3 to the power n for this case where it is purely imaginary. So the modulus of z3 to the power of n, where n is actually 15, okay, it is going to be square root of 3 to the power of 15. And I'm going to just rewrite this as square root of 3 to the power of 14, then square root of 3. Pressing this into the calculator, this will be giving me a 2187 square root of 3, which is according to what the question says. We want it to be in the form of k square root of 3. So k in this case is this, okay, 2187. And according to the question, we also want the argument of z3 to the power of n. In fact, this n here is 15, so it is totally okay if I were to just write this as 15. Maybe I should do that. So I'm going to write this as 15 here, and this is 15, okay, because n is supposed to be 15. And what is the argument that we are talking about? We are talking about 7 times n, which is 15 pi over 30. And this is giving us a 7 pi over 2. And if I were to just minus 2 pi to this, I will be getting a few times, okay? If I were to minus 2 pi to this a few times to get it into an argument that is between minus pi and pi, that will be negative pi over 2. Okay, we are done with question number 3. Let's move on and take a look at question number 4, which is actually here. It is a summation question. Okay, so in question number 4 over here, the very first part is requiring us to rewrite that expression in its partial fraction form. So we have in part A, we have this 9r squared plus 3r minus 2. 1 over this, which is in the denominator, 9r squared plus 3r minus 2. we want to rewrite this into its partial fraction. So for the denominator, if I were to factorize this, we will have a 3r minus 1 and a 3r plus 2. So we are going to let this over here be equal to a over 3r minus 1 plus b over 3r plus 2. And we're going to make use of the cover-up rule that is going to be helping us to find a and b. So to find a, I'm going to cover up 3r minus 1. I'll replace all this r here by 1 over 3. So it's going to be 1 over 3 times of 1 over 3, then plus 2. So a here is equal to 1 over 3. To find b, we are going to cover up 3r plus 2, and we're going to replace all this r here by negative 2 over 3. So it's going to be 1 over, covering up this, replacing this by negative 2 over 3. It is going to be 3 times of negative 2 over 3 minus 1. This is minus 1 over 3. So we have this 1 over 9r squared plus 3r minus 2 to be equal to 1 over 3 of 3r minus 1 minus 1 over 3 of 3r plus 2. Okay, this is our partial fraction form for part A. And in part B, we are supposed to be evaluating that expression over there. And for that expression, within the sigma notation, we have this. Okay, so pretty obvious what we are supposed to be doing. We are going to be rewriting the expression that is within the sigma notation by this. Let me just rewrite this here first. Okay, so I can reuse this. So from part A, we have found out that this is equal to this expression over here. I must well just factorize out 1 over 3, which will be giving us a 1 over 3r minus 1 minus 1 over 3r plus 2. Okay, we have this over here. Now I can erase this, which is from the partial fraction that we have just done. And I'm going to try to find for part B, summation from r starting from m to 3m of 1 over 9r squared plus 3r minus 2. So replacing this by this and factorizing out 1 over 3, we will be having a 1 over 3 summation from r is equal to m to 3m of 1 over 3r minus 1 minus 1 over 3r plus 2. Okay, it is from this expression over here. We are going to make use of the method of difference presentation to try to evaluate this summation further. So it is going to be equal to, let's try, okay. We are going to replace this r by m. That's the very first r. So it's going to be 1 over 3m minus 1 minus 1 over 3m plus 2. This is when r is equal to m, and we are going to replace r by m plus 1 for the second row. So replacing r by m plus 1, we will be getting the second row here to be 3m plus 1, then minus 1. Simplifying it, it is going to be 3m plus 2. Then minus away 1 over 3m plus, what do I have here? Plus 5. Okay, let me just write it down. Here we have let r be equal to m. Here we have let r be equal to m plus 1. Let me write down one more row, which is letting r be equal to m plus 2. And this will be resulting for me a 1 over 3m plus 5. If I were to replace this r by m plus 2, then minus away, replacing this r by m plus 2, I will have a 1 over 3m plus 8. So we can see a pattern that is happening, which is something that we are expecting when we are on the right track applying the method of difference, which is this pattern is happening. Okay, this pattern of cancellation is happening. We're going to verify this pattern. We see that 2 rows gives us 1 cancellation. So I'm going to write down the last 2 rows for the verification. And the last 2 rows will be, the second last row will be this 3m minus 1. And the very last row will be when r is equal to 3m. So let me write it down. When r is equal to 3m minus 1, we will be getting a 1 over 9m minus 4 minus 1 over 9m minus 1. And when r is equal to 3m, we will have a 1 over 9m minus 1 minus 1 over 9m plus 2. So we are seeing the same kind of cancellation. We have verified that, which is this pattern over here. Okay, it continues all the way until the very, very last 2 rows. I'm better writing the dot, okay, because I'm not writing those that are in between. I'm not able to anyway. So we can imagine that all those that are in between, they will disappear, leaving us with just this expression here and this expression here. Let's not forget about the negative. So we have this that is going to be left, and which means that this is going to be equal to 1 over 3 of this. Okay, 1 over 3m minus 1 minus 1 over 9m plus 2. This could have been my answer if not because the question actually says that we are supposed to write down our answers in a single fraction in terms of m. Okay, so too bad. We need to continue with this, which is 1 over 3. Rewriting this into a single fraction, 9m plus 2 minus away 3m minus 1 divided by 3m minus 1, 9m plus 2. And this will lead me to a 6m plus 3 over 3, which is from here, of 3m minus 1, 9m plus 2, which if I were to cancel away the 3 from the numerator and the denominator, my final answer is 2m plus 1 over 3m minus 1 multiplied by 9m plus 2, and I'm running out of space. So that is my answer for part B. I think for me personally, I find part C sort of tricky, okay? Because for part C, let me just write down part C here because I will need to make use of part B for my imagination, okay? So for part C over here, we are supposed to evaluate the sum to infinity of this expression, but from 1 to infinity. Okay, it is going to be starting from 1. And I cannot possibly make use of this directly because if I were to replace this m by 1, the result here is summing from 1 to 3. Okay, but we need 1 to infinity. Okay, so what I think is a good way for us to be evaluating this is for us to make use of what we have observed here as a method of difference pattern to first try to evaluate for ourselves a new summation that starts from 1 to n first. So this 1 over 9r squared plus 3r minus 2. If I can just imagine what that is supposed to be happening, okay? I mean, I'm not expecting myself to be required to write too much, but if there's no choice, if you need to write down a bit more, by all means do so. But looking at the 1-mark question, we know our working is not going to be very long. So if I can just imagine based on this that is here, right? The next line is going to be 1 over 3, sum from r is equal to 1 to n of 1 over 3r minus 1 minus 1 over 3r plus 2. And when I try to expand according to the method of difference, I will be left with this term and this term. So in between will all disappear. It will still be applied to this. So if I can imagine this, right, that means the first one is when r is equal to 1, which is going to be 1 over 3 times 1 minus 1. And I can go all the way until the very last term here, which will stay. In between will all be disappeared according to what I'm seeing here. So the last one is going to be minus 1 over, replacing r by n, it is going to be 3n minus 1. So we are, in a way, expecting something that is like this. Sorry, the last term is going to be 3n plus 2. So this is incorrect. So this will be 3n plus 2. Okay, because this very last term is going to be from here, where r is replaced by 3m. So this is going to be from here, and I'm going to replace this r by n. So we have this in between will disappear, which means that from observation, right, we are supposed to be able to see this to be 1 over 3. Then the first term, which is going to be 1 over 3 times of 1 minus 1, minus away this term, which is 1 over 3n plus 2. Okay, we want to observe this from the first part. Okay, so this is just all supposed to be my imagination. Okay, let me erase this so that I can continue to write. So from part B, hopefully we will be able to sort of foresee that my answer is going to be something that is like this, which is going to be equal to 1 over 3 of 1 over 2 minus 1 over 3n plus 2. So based on this that we have, then we can work out r starting from 1 all the way until infinity by letting n goes to infinity. So this 9r squared plus 3r minus 2 is going to be equal to 1 over 3, 1 over 2 minus 0. So my answer here is 1 over 6. A little bit of a twist from the usual summation question that we have been working in our school, but yeah, it's just a 1 mark question. Okay, so I find that it is a little bit strange. So anyway, we will not need this. Let's erase this and work on the last part, part D. In part D, let me just write down the numbering here. In part D, we are supposed to find the smallest value of n for which the summation from r is equal to 1 all the way until n of 1 over 9r squared plus 3r minus 2. I'm glad we did this. Okay, so now we actually have the expression to represent this. We want to find the smallest value of n for which this differs from the sum to infinity, which is differs from the sum to infinity, starting from 1 all the way until infinity of 1 over 9r squared plus 3r minus 2. Because the question chose to use the word differs. Okay, so it means that we are not sure which one is going to be bigger. So we are going to put a modulus to this. So we are looking at the absolute difference, and this difference is supposed to be less than 0.004. So this over here is this, which is 1 over 3, 1 over 2 minus 1 over 3n plus 2. Minus sum to infinity, we have just worked it out. It is 1 over 6. So I will have a 1 over 6 here. Is supposed to be less than 0.004. Within this modulus, if I were to just simplify this, I'm going to be getting a minus 1 over 9n plus 6. And I think I'm going to move this over to the left-hand side. Negative 0.04 is supposed to be less than 0. So what I'm going to try to do is to find the smallest value of n such that this expression here is less than 0. And to do this, I am going to once again make use of my calculator. So on my calculator, let me trigger this. I'm going to go back to y1 again, and I will press this into the left-hand side of y1. So let me press it in. Okay, this is what I've pressed in. I'm going to trigger the table again. So I've triggered table. What I'm looking out for is when this expression here is less than 0, negative. And this expression is going to be represented by y1, where x here represents the different integer values for n. So let me scroll down to see when y1 is going to be negative. Okay, so not yet. Not yet. Let's see when will it be negative. Still no. Okay, we are starting to see some negative values here. In fact, this is the first x that's going to cause y1 to be negative. I'm going to plant that into a table in my script. So x there, I'm going to be representing it by n on the table that I'm going to draw in my script. And y1, I am going to write it down here, which is going to be modulus of minus 1 over 9n plus 6 minus 0.004. So according to what I'm seeing there, when n is equal to 27, okay, when n is equal to 27, we have here a 1.6 times 10 to the power of minus 5. It is still a positive number, small but positive. Then when it is 28, we have a negative 1 times 10 to the power of minus 4. My first negative number. And when it is 29, we have a minus, here minus 3 times 10 to the power of minus 4. So all these n's are going to cause this expression to be negative. So the smallest possible n that the question wants is going to be equal to 28. Because the question did say this. Let me just take a look at the question again. The smallest value of n, okay, such that this is less than 0. It can be 28, it can be 29, and so on. The smallest is going to be 28. So this is question number 4. Let's move on to the next question. Okay, let's take a look at question number 5, which I've already drawn one of the diagrams here on the board. We are supposed to show by integration that the volume of this spherical cap, which is this one that is over here, is 1 over 3 pi r h square 3r minus h. R is this r, which is going to be the radius of the circle. This is a circle's equation, right? So this is the radius of the circle, which means that this, which is going to be radius, I mean for this circle, the center is at the origin, right? So this is going to be the radius, which means that this point here will have a y coordinate of r. And for this spherical cap, according to what the question says, this height of the spherical cap here is h. And they also gave me the y coordinate of this, okay, which is this line here, y is equal to r minus h. So the y coordinate that is for this particular point here is actually r minus h. You can take r minus away h. You can actually derive it yourself. In order for us to find this volume, what we are going to try to do is we are going to try to take this portion of the graph, okay, and we are going to rotate it about the y-axis. So we are going to be looking at just this region here, okay, being rotated about the y-axis in order for us to find the volume of this spherical cap. So the first thing that I'm going to do for part A will be taking this equation over here and making x the subject, because our intention is to try to revolve this region about the y-axis. So x squared is going to be equal to r squared minus y squared, which means that x is plus or minus square root of r squared minus y squared. And because we are taking this portion of the graph, okay, which is positive x, so this portion of the graph, we are going to go for x is equal to positive square root of r squared minus y squared. X is this, and the volume of this spherical cap is going to be pi integration from this y coordinate r minus h all the way until this y coordinate r of this square root of r squared minus y squared square dy. We are rotating this with respect to the y-axis. So we have a pi integration of r minus h to r square root square. I'm going to be left with r squared minus y squared dy. So integrating this is going to be r squared y. R squared is just a constant, okay? So it is integrating a constant r squared y minus away y to the power 3 over 3. We are going to be substituting r minus h and r into this as the lower and upper limits. So we have a pi. Let me do the substitution, okay? So substituting this in, it is going to be r squared multiplied by r minus r to the power 3 over 3. Minus away, substituting this in, we have a r squared, then y is going to be replaced by r minus h. Then minus away this y, which is going to be replaced by r minus h to the power of 3 over 3. Okay, we have this, which is going to be pi. Let me try to do a little bit of evaluation over here, okay? So this is going to be r to the power 3 minus 1 over 3 r to the power 3. This gives us a 2 over 3 r to the power of 3. Then if I were to expand this, r to the power of 3 minus r to the power of 3, this is going to be RH with a minus here. We will have this as a r square multiplied by this, we will have a plus r square h minus 1 over 3 of this, which I'm going to expand it using binomial expansion, which is going to be giving us a r to the power of 3 minus 3r square h plus 3rh square plus minus h. Here will be minus h to the power of 3. So we have this, which I'm going to leave it to you guys to continue simplifying this, okay? If you were to simplify this fully, you will end up with a 1 over 3 pi h square and 3r minus h, which is what the question is supposed to be asking us to show. And we will be needing this. So let me write down this somewhere so we can keep this information, okay? So the volume of this, okay, of the volume of this is this over here, which is actually is also inside the question. This is equal to 1 over 3 pi h square 3r minus h. Okay, we have this. Let's move on to look at the next part of the question, which is actually the slightly more interesting part. Okay, so in the next part of the question, we are looking at this ornament. And this ornament is this one over here, okay, which is actually going to be from a sphere, and this part is chopped off, this part is chopped off. This is what we have. It is given to us that the volume of the sphere is this. This is a general formula for the volume, and we are supposed to find an equation that is going to be satisfying P, and hence find the value of P, when I'm also given that the volume of the ornament is 2402 pi cm cube. So this volume here, 3402 pi cm cube. And we are also given that the height of this ornament, sorry, not ornament, not the height of the ornament, but the height of the cap here, the spherical cap over here. This height here is given to us from the picture as P. And the height of this other spherical cap, which is at the bottom, is 3P. So this is my plan, okay? My plan is to make use of the volume of the sphere, minus away the volume of this cap, and minus away the volume of this cap. Okay, this is, I will call it the top cap. Let me just write it down here. This, I will call it the top cap. This, I'm going to call it the bottom cap. Okay, so we have two caps over here, and actually we do have the general formula to find the volume of the two caps. That is from the first part, right? From the first part, as long as we have a sphere with radius r and a cap of height h, the volume is going to be this, which means that for the volume of the top cap, in fact, the top and bottom is also described to us by the question, so I didn't even need to name these myself as top and bottom, so I'm going to just use the question's definition, okay? So, in order for us to find the, let's look at part B, the volume of the top cap, top spherical cap. Okay, it is going to be making use of this. It is going to be 1 over 3 pi h, which is the height. So it's going to be P square. Then 3r, which is the radius of the sphere. In this case, it is 15. So here, 3 times 15 minus h, which is P. Okay, this is equal to 1 over 3 pi P square, 45 minus P. And we want to find the volume of the bottom cap, which is actually the same. This is a sphere, okay? Top and bottom, they're actually going to be calculated using the same way for the cap. So for this cap here, it is going to be 1 over 3. I'm using the same formula that we have derived in the previous part. Pi, the height of the cap in this case is 3p square. Then 3 times of r, which is the radius. Once again, we have a 15. That minus the height of the cap, which is 3p. This is equal to 3 pi p square, 45 minus 3p. The volume of the top cap, the volume of the bottom cap. And we are going to also find the volume of the full sphere, the entire thing, which is going to be 4 over 3 pi r cube. This is 4500 pi. And the volume of the ornament that is given to us, let me just write it out. The volume of the ornament, according to the question, is this 3402 pi. And how do we calculate this? We're going to take the volume of the sphere, which is going to be 4500 pi, minus away the volume of the top cap, which is 1 over 3 pi p square, 45 minus p, minus away the volume of the bottom cap, 3 pi p square, 45 minus 3p. This is going to be 3402 pi. So all the pi's over here can be cancelled. And if I were to just leave it to you guys to try to simplify this, you will actually derive at an equation that is going to be similar to this. 28p to the power of 3 minus 450p squared plus 3294 is equal to 0. In fact, this is what the question was saying. We are supposed to find a cubic equation satisfied by P. So this is that cubic equation satisfied by P, and we're going to press this directly into the calculator to solve for P. So from our graphing calculator to solve for P, we are going to be getting P to be equal to negative 2.5158, or P to be equal to 3, or P to be equal to 15.587. Okay, we are going to be just keeping one of the values. Okay, I think this is easy to reject. So why is this rejected? Because P, which is the height of the cap, it must be a positive number. Okay, so I'm going to be rejecting a negative number, but should we be accepting this or rejecting this? If you were to look at the diagram that is given to us, right, this is the top cap, this is the bottom cap. 15 is going to be this, the radius of the sphere. So this P here, yeah, we cannot allow this P to be bigger than 15, right? If it is bigger than 15, this top cap will become like top eating to the bottom portion of the cap. You know, so we have to reject this. So NA, because we want to make sure that P is also a number that is less than 15. So P is equal to 3 is my selected value. That will be, yeah, will be the answer for part B. And I think part C is, we need to put on our thinking cap, okay? Because for part C, let's just take a quick look at part C. So far, right, we have already worked out the value for P, okay? Let me just write it down here for us. So this P here, P, we have worked it out to be 3. Okay, let me erase this that we have here. Yep, I don't think we need this. Okay, maybe let me just keep some of it first. Okay, let me erase this. What I want to do is to do a quick analysis together with you guys, okay? So, yep, let me erase this whole chunk over here in order for us to work on the last part. Okay, but we will definitely keep this, okay? So, putting on our thinking cap, let's think about how can we satisfy a condition that is described to us by C, okay? In part C, we need an ornament, and according to the question, this is a different ornament. So it cannot be exactly the same as this. And this ornament is going to be from a sphere with a radius of 15. So we are looking at the same kind of shape. Let me just draw it here. Okay, we are still looking at one where the radius of the sphere is 15. Okay, this volume, this new volume of this second ornament has to be less than the volume of this first ornament. And the top face of the second ornament has to be the same radius as this. So the top must be the same as this. Let me just draw it to like symbolize that it is the same. Okay, so this is going to be the same as this. Okay, and the bottom face of the second ornament must be the same as this. Okay, so it must be like this, the same as this. Okay, that's a strange thing. Okay, if the top face of the top cap is if the radius of the top cap is the same as the previous one, and the radius of the bottom cap is also the same as the previous one, how can then this volume over here, well, for the second ornament, be less than this? Okay? And that is why we need to put on our thinking cap. Because in order for this to happen, we are going to, like if you think about it, okay, how can this be smaller than this? Yet I retain the radius of the bottom cap. So what we are going to do is we are going to shift this length here up. Okay, for example, like this. Okay, not the best diagram, but for example, something that is like vertically up. Okay, this is not vertical, but I'm aiming to shift this vertically up, okay? So that this can be the same as this, which means that if I can shift this vertically up to be something that is like this, okay, so this has the same length as this. Okay, so the radius is supposed to be the same. Then I will be having a second ornament that is going to be from a sphere with radius as 15, with the radius of the top cap to be the same as this, and the radius of the bottom cap to be the same as this, and the volume is less than this. This is what the question is saying. So in order for me to find this volume, I am going to make use of the volume of this second ornament. Okay, I'm going to make use of this cap here. Okay, this cap here, which is this, here to here. Okay, which is going to be the same as, because we have already seen just now, right? This is 3p. Okay, so if I were to shift this up, this here is still going to be 3p. And what is p? P is 3. So this is supposed to be 3 times 3 for the height of this, and then minus away this, which is p, and this is going to be equal to 3. Okay, so this is how I'm going to find the volume of the second ornament or the new ornament. So the volume of this second ornament is going to be the bigger cap, making use of this. We will have a 1 over 3 pi height is going to be 3 times 3. So 3 times 3 square, then 3 times r, it is going to be 15, minus the height is again 3 times 3. So 3 times 3 minus away this portion, this minus away this. So this portion is 1 over 3 pi. P is the height. So the height is 3 square, and 3 times of the radius of the sphere minus away the height, which is 3 again. And I will derive at my answer 846 pi.